Hello, in this video I will demonstrate to you how to use DMA multiplexer in combination with USART, external interrupts and timers in STM32C0 microcontroller. Prerequisites. We'll use Nucleo C031C6 board and we'll connect this board to PC using micro USB cable. Concerning software, we'll need STM32Cube IDE in version 1.10.1 at least, and STM32C0 Cube library in version 1.0.0. Here is a simple description of our lab. So on the left side we can see the block diagram of the complete system. So we'll use timer 1 in PWM mode on its channel 1 with period set to 100 milliseconds and flexible duty cycle. The output of this channel 1 will be redirected to PA5 pin, where we can see as well the green LED connected on the board, and the pulse value of this timer, which is stored in capture compare register 1 CCR1, will be transferred from internal SRAM buffer using DMA to this register on the synchronization signal coming from DMA multiplexer, which would be triggered by external pulses coming from PC13 pin. This PC13 is a place where we have blue button connected on our board. At the end of this DMA transfer between SRAM buffer and timer 1, we will have another synchronization signal which would synchronize another DMA transfer, this time from the TX buffer located again in the SRAM memory to USART2 in order to display some text messages. It will be DC space number of the percent of duty cycle which is currently visible on this PA5 pin. The interesting thing is that this transfer synchronized by DMA multiplexer will contain always 9 characters, so complete row from this TX buffer, and it is a new feature coming from this DMA multiplexer implementation which is available with an STM32C0. So let's have a look on the more details about the application. So timer 1 will be configured in PWM mode to work in 10 Hz output signal on its channel 1, redirected to PA5 with programmable duty cycle, which is marked as pulse. We can observe it on our green LED on the board. All the transfers between SRAM buffer to timer 1 capture compare register 1 will be synchronized by the external interrupt 13 signal coming from the blue button. So each blue button press will trigger the copying of the new pulse value from the SRAM buffer to timer 1 capture compare register 1. At the end of this transfer, DMA multiplexer will generate an event which would trigger another transfer from SRAM buffer to USART2. And USART2 will be configured as asynchronous interface on PA2 PA3 pins connected to our onboard ST-Link, so it will be possible to observe the data via the virtual COM port. And the parameters, it will be 115,000 bits per second, 8-bit data, 1 stop bit, and no parity. Those are the default settings in CubeMX and Cube IDE. Let's create a new project with an STM32 Cube IDE. I will use this path as a workspace location. And I need to create a new project, so I will go to File, New, STM32 project. As you can see, there is already some existing projects, so we can have multiple projects within one workspace, which is pretty convenient to switch from one to the other. So we need to specify the part number. It is STM32C0 31C6T microcontroller, so I would specify C031C6. And now we can see our Nucleo board is over here, so this is our part number. I click next. I need to specify the name, so I would propose TIM_XTI _USART _DMAMUX and press finish. Let's start from the pinout configuration. So PC13, it would be our trigger of the DMA transfer from SRAM to timer 1. So I would just click left button on mouse over this pin and select the last option, GPIO_XTI13. Then from system and core, I will select GPIO and this line, and I will check whether it is external interrupt mode with rising edge trigger detection, which is our desired configuration. Everything is correct, so I will not change it. And then within NVIC, and from the NVIC configuration, I need to enable this interrupt. Then let's switch to the timer 1 configuration. So I go to the timers, timer 1. It will be standalone timer, so we don't need to take care about the slave mode, trigger source. We just need to configure the clock source to internal clock and channel 1 to PWM generation. Then within DMA settings, I would add timer 1 channel 1 transfer, and I would change it to circular. I would change this direction to the opposite one, so from memory to peripheral, because we will transfer some values to the timer from the memory. And I will change the data size from half word to word on both sides, and I would keep this memory incrementation address. Then in DMAMUX below, we need to enable synchronization coming from this XTI13. So this synchronization signal should be XTI13, rising edge. And then we need to enable the event. So we need to generate the signal which would trigger another DMA transfer from SRAM buffer to USART2, which we'll take care a bit later on. So we've got the proper configuration of the DMA for timer 1. Now we can configure its parameters. So within parameter settings, we need to configure its work to 10 Hz output signal. The timer 1 is clocked by the default clock, which is 12 MHz coming from HSI 48 MHz divided by 4. So we need to divide those 12 MHz, for example, by 12,000. So we'll use prescaler as 11,999 because we are counting from 0. And we'll set the period to 100, so we need to write 99 because we are counting from 0. So in this case, when we use those two components, we'll have 10 Hz signal as an output of the timer 1 on its channel 1. Pulse value I would keep 0, as we will modify it via DMA from the SRAM buffer. So all of the settings of timer 1 are done. Now we need to do some pin remapping because PA0 is not our desired pin. We would like to have this function on PA5 where our green LED is connected. To make a remap, I need to go with the cursor of mouse over the pin, press the Ctrl on the keyboard, left button on mouse, and now I can see the alternate location. Then I need to drag this function to desired pin, in my case PA5, and release Ctrl and then left button on mouse. Remap is done. The last point from the configuration is a configuration of the USART tool. So I need to go to connectivity, USART tool. I need to select the mode as asynchronous. Those two pins are correct, PA2 and PA3. Those ones are connected to ST-Link on our Nucleo board. I need to configure the DMA settings. Click Add. We will send the data over UART, so I will select USART to RTX direction only. It will be from memory to peripheral, so it's correct. We will use circular mode, we will use bytes and incrementation on memory side. And again, we need to configure somehow the DMAMUX. So we will use synchronization coming from the DMA transfer between USART cut. We'll use the synchronization between SRAM2 and timer2. Sorry, cut. We will use a synchronization from the DMA transfer between SRAM buffer and timer1. So as a signal, I will select DMA1 channel 1. It is pretty easy to find it because it is the only active. We can check whether it is exactly this one, DMA1 channel 1. Yes. So we've got the source of synchronism, and we need to specify the request number. So the number of the transfer, which would be as an effect of this trigger. So it will be 9. It is the length of the single row of text we would like to display on the USART on each update on timer 1 pulse value. Okay, so this DMA configuration is done. We can have a look on the parameter settings, but we will keep all of the default ones. So 115,000 bits per second, 8-bit data, no parity, and 1 stop bit. We are ready to generate the project. So we can go to Project Manager just to verify whether everything is okay. In case no change on the project name on its location, we can generate it, for example, by clicking this gear icon. When it's done, we can specify some variables which we will use within this exercise. So the first one would be the table which would contain the pulse values for the timer 1. So tens, 0, 10, 20, 30, 40, 50, 60, 70, 80, and 90. And then we need to specify the table which would contain the data which we would like to send over the USART. So tx underscore data. It will be to D table. 10 rows, 9 characters each. And now we need to specify the first row, and then we will use the copy paste. So we can send something like this: DC 0%, and then new line carriage return. And then we need to copy it 10 times. 9 times, in fact. 1, 2, 3, 4, 5, 6, 7, 8, 9. And just change this one space into the proper value of the duty cycle. $50, $40, $30, $20, and one more, 10. Let's have a look once again. 10, 20, 40, 50, 60, 70, 80, and 90. This cynical one is not here. Okay. So this is those are the variables we would like to use. Please have a look that I located them into the user code section. Otherwise, those would be deleted in case of any project regeneration. The next point on our side is a verification whether the initialization of the peripherals are properly done by the Cube IDE. DMA should be the first one above all of other peripherals which are working with DMA, so timer 1 and USART 2. And this is the case, so everything is correct. And we are ready to activate the peripherals. As timer 1 will in fact somehow trigger the DMA transfers from SRAM to USART 2, we can start from USART. So HAL underscore UART, in fact, underscore T, because we would like to transmit data. And now we need to select the function of the DMA. USART 2, then the data, so this is TX data, and the size we can use so this is the first one, and the second one concerning the timer. So HAL timer PWM control space start with DMA. Timer 1 channel 1 pulses and 10, and that's it. In case you are lost, in case in case you do not know which arguments you should put into the function, you can just go with the mouse cursor over the function name and you can see the brief description of the arguments needed. So the coding is done. I can compile the code using this hammer icon. No errors, no warnings. We can see as well the usage of the memory. RAM is 17% and flash is more or less 48% almost. Now we are ready to start a debug session, so I click on this back icon. My board is already connected. I click OK. And now, before we will start, let's configure the internal terminal window so we can observe the data coming from our virtual COM port. So to do this, I will go below and I would select from this Open Console window Common Shell Console. As a connection type, I would select the serial port. Connection name, we will specify the new one. So let's put labs_terminal. Serial port, it should be the one which has been assigned to our virtual COM port on ST-Link. Usually it is the highest possible number. Baud rate, as we kept default, it is exactly the same, 115K, 8-bit data, no parity and 1 stop bit. I press finish and I press OK. Now we can see below the console, the terminal is connected, it's ready. Here on the right side we can see 2 new icons, connect, which is disabled because it's already connected, and disconnect. So we can disconnect our terminal from the COM port. So now we are fully ready to run the application. So I will just press resume. And now if I would press the blue button, I can see different string displayed, and again I can see some activities of my LED. So this is the duty cycle changed from 0% up to 90%. So I can see that at 90% is almost constantly on, while on 0% is completely off. 10% is visibly blinking. So all is working properly as expected. So we can close this application at the moment. So thank you very much for your attention.